Okay, let's get started. So this is finishing up that example. The last one that we put up on Tuesday. So I don't know if anybody tried it, but we'll go through it today and we'll work out sort of the full expression of what we're going to do. So perhaps you can actually see how to solve this problem. And then we'll put up a MATLAB file to help you kind of come up with it. So let's start off with the different tests and what is conveyed from each test. First thing is the DC test. And remember, this is a Y-connected machine, so I included that in this copy. Y-connected in DC land. Let me make sure, where's the... In DC land, we're going to show all three windings and only show the elements that aren't shorted out. This is R1, R1. R1 is a three-phase machine, so we have three windings, which means we have three R1 resistors. Our DC is applied across this terminal, right? And if you look at the DC test, we have 13.6 volts. And it doesn't really matter plus to minus with DC, but we'll just include it. And then our current is 28.0 amps going through there. So from Ohm's law, we can rewrite this circuit and simplify it down a little bit. 13.6. We go through one R1, another R1, and then we return back to the power source. And the current through here is 28 amps. So 13.6 divided by 28 equals 2R1, which means R1 is equal to 13.6 over 2 times 28. All right, that's the first one that you solve for, and you can immediately solve for one of the parameters you're trying to calculate. All right, any questions on that? Because the next two tests, we're only going to get part of the puzzle. We're going to need to do get the other test going through and then do some calculations and use one of our tables to give us the ratio of X1 and X2 to the locked rotor currents, and then go ahead and process those. So if there are no questions, let's move on to the no load test. I'm not sure why that's shaking so much. So the no load test, if you recall, and again, I recommend that you do this for any type of test that you're trying to use to solve parameters. Go ahead and show what parameters you're going to be able to solve for with that test. All the other parameters are not included. So for the no load test, we have R1 is in the picture. We have, whoops. Okay. What's going on? Sorry about this. Seems like there's a little bit of a What's wrong with whiteboard? Well, it looks like whiteboard just crashed. Sorry about that. Try that again. Wow, that was a bad crash. Let's see if it's running in the background. I don't see. I'm not sure why whiteboard won't start. So I'm going to kill both of these. Try that again. All you PC users, do you remember Task manager, or am I doing something completely out in left field? Maybe. You could say no. Just
Wish it was like the old one. It's so much weirder now.
it is a little goofy, but it gets the job done. When in doubt, use task manager. That kills things. So you can see I tried to stop it, but it said it was still running in the background, so you can get more information. Okay, so here's our one. Here is JX1. And here is JXM. And remember, R2 over S under no load conditions is just R2. And JX2 is pretty small. So under our I'm sorry, back up. R2 over S is really large because S is essentially 0. So you have no current flow that flows in that rotor circuit, which means I2 is equal to 0. So we can neglect any current going through the rotor circuit and just show the stator circuit. So now I'm going to add my elements. I have plus to minus 208 divided by the square root of 3 at an angle of 0, because that's what I know. Remember, magnitude and angle for current and voltage. My current is 8.17, and the angle at this point is a question mark because I don't have enough information to be given that. So I put that as a question mark. My input power, I do have that, is going to be equal to 420 watts. Okay. So now I can go ahead and do a power triangle to get the angle of current, because the angle between P and S is the same angle between the voltage and the current. So my power triangle, this is going to be a lagging power factor. So this is 420. Nobody's giggling. One person gets it, so 2 people get it. Okay. What's that? Is that the joke then? So everybody's gonna have a good time that day. So anybody doing the healthy high? Oh, how convenient, right? You know what the healthy high is? Maybe they're not doing it this year. It's a 5K.
They're doing it.
Oh, it's 4.2K now? Oh,
Yeah.
it's even easier.
I want to say it's like $15 to do it.
They charge you $15. It used to be free, but
I know I've been told it's $15 to compete in the 5K or whatever it is.
yeah, maybe Pascal will run it with you guys. So. All right. Well, check it out if you want something fun, because it's always good to do something healthy and fun, and you can do whatever you want. But I've done it a few times. It was a lot of fun. There's a lot of energy, and it's pretty crowded. When I did it, it was a 5 and a 10K with the options. I don't remember the 4.2, but that was a couple years ago. All right, so what is S in going to be equal to? Remember, the power that is measured is the 3-phase power. You can't just run one single phase voltage. This machine has to rotate. So when you apply that voltage, that 208, that voltage has to be applied to all 3 phases to make sure that it rotates as if it would normally be operating. So that 420 watts is total real power under no load conditions. My input then is going to be equal to 208 over the square root of 3 times 8.17, because I'm just looking at magnitude, right? I'm not worrying about the angle. I'm just doing the magnitude. Is there anything missing from S in? Do I have all my equation correct? We talked about this in the last class. Don't you have 3 phases? And this is the power for one single phase. Don't I need to multiply that by 3 to get the total power? So now my theta, no load, can be found. I can SOHCAHTOA it, right? Is the inverse cosine of 420 over my input power. So once I have that, now I know what the magnitude and angle of the voltage is. I know what the magnitude of the voltage and the current are. And since this is a single phase equivalent, I can solve for the single phase impedances or the individual impedances. And I know that Z no load is equal to R1 plus J X1 plus XM, right? And that is going to be equal to the voltage divided by the current. Don't forget, though, this is the case where you have to decide if you're going to put a positive or a negative with the angle for theta no load. And because this is a lagging power factor, the current angle needs to be lagging power factor. What lags what? Current lags the voltage. At the voltage at an angle of 0, what kind of an angle does the current need to be at? Negative. So that's the value. I don't need R1. So all I'm going to do, because I've already solved for it, I'm going to solve for the imaginary part of Z no load and set that equal to X1 plus XM. So take the imaginary part, that's going to be equal to X1 plus XM. One equation, two unknowns. So I have to do another equation, which means I have to get my results from my locked rotor test. And my locked rotor test, remember, in that case, my slip is equal to 1. So X2 and R2 are much, much smaller than XM. So we're going to assume that there's no current that goes into that magnetizing one. That's also why we apply a pretty small voltage to help it make sure that there's no current. And what I'm left with is R1, JX1, JX2, and R2. That's my equivalent circuit. I'm going to apply my voltage, 25 divided by the square root of 3 at an angle of 0 is my applied voltage. My current is 27.9 at an angle of question mark, just like we had before. My input power is going to be equal to 920 watts. So I had to do a power triangle before. I have to do one here as well, because I need to get that angle with the current. This is the only way I can get that angle. So my power triangle is going to be 3 times 25 over the square root of 3 times 27.9 is equal to my locked rotor current, or locked rotor input power. And my theta locked rotor can be found by taking the inverse cosine of 920. And I'll call this, I'll add on the locked rotor over here to make sure that we differentiate between the two. Okay. So now I can take my voltage, 25 over the square root of 3 at an angle of 0, divide that by my current, 27.9 at an angle of minus theta locked rotor. And now that's just going to be equal to the Thevenin equivalent of that particular machine under those conditions, which is just equal to R1 plus R2 plus JX1 plus X2. Now be careful, because, well, let's do the real part. So the real part, and let's call this Z locked rotor. The real part of Z locked rotor is going to be equal to R1 plus R2. We already solved for R1 from the DC test, so I can solve for R2 is equal to the real part of the Z locked rotor minus R1. To do the X1 plus X2, we have to be careful. So what we're going to do is we're going to pull out the imaginary part of Z lock rotor and set that equal to X1 plus X2. We need to be careful because the test, and we said not to burn up the motor, we should apply a frequency that is much lower than rated. So the frequency for the locked rotor test was equal to 15 hertz. We need to correct that at 60 hertz because this motor is intended to operate in a 60 hertz system. So our correction factor is equal to 60 over 15 or 4. Okay, because X sub L is equal to omega or 2 pi F times L. So if my frequency goes up by a factor of 4, I'm just going to multiply that out. The correction factor. So this is the imaginary part. What I need to do is X1 plus X2 has to be multiplied by my correction factor to get everything in 60 hertz land. Once I have that, I've got to look at the NEMA design characteristic, and I have to go through my table. So my table, where's my table? Is equal to that. NEMA design A tells me that both X1 and X2 have the same value. They're equal to 1/2 the lock rotor reactance. So I can go back to here and say X1 plus X2, and maybe I'll put these corrected. So we'll just add a C, is going to be equal to X lock rotor multiplied by my correction factor, but divided by 2, right? Because 50% of something is the same thing as dividing by 2. And now I said a plus, it should be equal to, sorry. This is equal. Oh, come on. Whiteboard is not being very good today. So let's try closing that again. Or maybe it's back. I don't know. Seems to be back. Let's try it. So X1 equals X2 is equal to my lock rotor value multiplied by correction factor divided by 2. Yes, sir. The NEMA design A, right? And X1 is equal to 0.5 XLR and X2 is equal to 0.5 XLR. So they're the same value and they're exactly half of the lock rotor reactance.
So was it given that it was designed?
Yep. If you look at the problem description, see 60 hertz design A in the second line. That's the information. Okay. So now we know what X1 is. From back before, X1 plus XM was equal to the imaginary part of Z no load. So XM is going to be equal to the imaginary part of Z no load minus XM, or X1, sorry, not XM. That's been corrected. And that's how you solve for the parameters. If it was a delta connected machine, you just have to be careful with your phase voltages. You know, at that point, it would be 208, not 208 below the square root of 3. And you would have to correct your currents. Just make sure you have your current set up. And then the last thing you would need to do is just make sure that you understand your R1s are going to be a little bit different. Yes, sir. Minus. Questions on this? Crystal clear? Here's how you do it in MATLAB. Did the DC test? Did the no load test? Did the lock rotor test? And you can see how I corrected my lock rotor. Then I did all my values. Now the problem description, just all the problem description has done is once I've done all this process, I have the entire circuit all laid out. So now I can find what's requested. Find the slip at pull-out torque and find the value of pull-out torque, which you can do the Thevenin equivalent approach, or you can just do the brute force approach, which is what we did last time. So here is all those parameters. You can see I did the V Thevenin approach. So I did the V Thevenin, and then I also just did the brute force approach and pulled it out that way. So you can do brute force. This does both of them. So if we run this, here's our value. Get this out of the way. So these are our value for our, whoops. Here's R1, R2, X1, X2, XM, our maximum torque using our V Thevenin approach and the corresponding slip max. And then also the slip max by doing it the brute force way. The brute force way just brings up this plot. So you can pull it from there. And this one looks quite a bit different, right? This is the NEMA Design A. Remember the NEMA Design A is going to have even, it's going to move its pull-out torque even closer to the full load value. So this one looks slightly different than the curves that we did before. But if you wanted to go back and change it, all you need to do is when I do my plot over here, my R2 value right here, I can just go ahead and multiply this by 2. So let's put that in. So I'm going to multiply this by 2. So let me hold this curve. Now I'm going to run it. So all I did was double R2. Nothing else has changed. There's R2. Looks more like a NEMA Design B than the first one. Okay. Questions on this? Make sense? Doesn't make sense? This is the type of stuff I'd expect you to be able to do on the test, right? Take these data, take the test data, and be able to calculate all those parameters. Yes, sir. You could, but it would take too long. So just use a Thevenin equivalent approach. That's the way I would do it. What do you think? You like the MATLAB stuff, or you still could take it or leave it? You're not sold yet? It's okay, you don't need to be. With
Still not a
MATLAB
big fan
or
of
without?
MATLAB.
Yeah, so that's the hard part about MATLAB is you can't write things and you can't show the detail. You have to be more specific. So I try to put things to detail like I magnitude, no load. That's what that stands for. But it follows exactly what we did on paper. So MATLAB, where if it has a falling down, is the equations don't look like if you were going to do it on paper and pencil, right? 25 divided by square root of 3. We just put 25 over square root of 3. instead of the way that this is written here. But again, it just keeps me honest, right? All those values, those plots, they kind of validate what we have. So let me change this back to 1 or no multiplication, just so that it doesn't confuse anybody. Okay. The last topic. Oops, did I just close that by accident? No. Starting an induction machine. It's pretty tough. Because remember, all you have in that circuit is you have your X2 and your value of R2. So it pulls in massive amounts of current to go ahead. And that's just the AC current. You also have a transient. Do you remember in EET, maybe 111 or EC, if you took it, whatever the 209 or 210 equivalent is? Anytime you have an RL circuit, depending on when you close in on the sine wave, you have a transient. It's going to develop a opposing transient to make sure that the current doesn't change instantaneously. So you have a transient and a steady state value. Yes, sir. Transient is just something that goes away with time. So over time, it disappears. Static means it doesn't change. Transient means it's changing. Okay. But it doesn't, another way to say it is dynamic. But the thing about dynamic is it's something that is always changing. It can stay away forever. Transient means it's changing, and then at some point it's going to go away. It's going to stop changing.
Paul, the screen you're sharing is, I think, like the presenter mode.
Yeah, sorry, I forgot to do the duplicate.
Okay, thank you.
All right, so this one shows what a startup would be. And if you take a look at it, this is for the first 10 cycles or so, right? 16.67 milliseconds is 1 cycle. So you'd be about 10 cycles. And this would be the lock rotor condition if it stays indefinitely. This thing is pulling over 600 amps peak, which is 450 or something like that, which this motor is definitely not designed to handle that level of current for that period of time. So what we need to do is we need to be able to analyze when our motor starts, how much current does it pull in? And the real reason why we need to know that, and this is more of a design application, whenever you have a motor, okay, you're going to be feeding it. Let's say it's being fed from a 480 volt bus. And there's a device called a contactor. I'm going to put it down over here. Anybody know what a contactor is? It's not a breaker.
It's a big relay.
Big relay? Sort of, yeah. It's something that's designed to open and close many times. So it can operate 1 million times, 2 million times, and it not gets damaged. So it can do that because it's designed mechanically to do that, open, close, but it can't interrupt fault current. So what you actually have is a fuse that if the motor experiences a fault, that contactor will not try to open and interrupt the current because it's actually going to get damaged. So one of the things that controls the opening or closing of this contactor is it actually steals power off here and does control power. And so what you'll see is this is typically 120 volt, and you'll have a push button. So you'll have a start push button where you'll hit the button here. And then what you'll do is you'll go to a contactor that is, this is the operate, we'll just call it operate. And that, when you hit the button, it picks up the operate, and then it will go ahead. And this actually has the contact that is over here. Okay. Now, this is not intended to be all knowing because when you hit a push button, it starts. You don't want to keep hitting the push button. So you do have something called a seal-in contact. And a seal-in says once that operate contact is picked up, then the seal-in will close as well. You also will have upstream here. You'll have a stop push button. And the stop push button pulls all the power away. So you can go ahead and interrupt that. So this contactor, you can see, is fed from power off this 480 volt bus here. It actually is fed right from here. So let's do it more accurately. The problem is that device here, this transformer, this contactor drops out if the voltage is less than 90% voltage. Well, this is 480, but this is being fed typically from some kind of a transformer. When I'm pulling 6 or 7 times the full load current, the voltage drop across here can be extremely high to the point where this contactor actually drops out. So you hit this push button start, and you let it go, and then all of a sudden the motor doesn't want to run. And that's because you've got too much voltage drop across it. And so how do you figure that out? It's based on this inrush or starting current. So we are going to look at inrush current and how some of the methods to mitigate that. So here is our equivalent circuit diagram. And remember, at a slip of 0, everything goes, or almost everything goes through here. Okay. And the voltage over here is equal to V nominal. So you're pulling in a lot of current. You don't have much because this R2 over S is a pretty small value. It's just R2, as a matter of fact. So I've got the steady state value here, and then I've got this decaying exponential. Don't worry too much about that. Well, actually, no, this is actually the steady state value. We would have a decaying exponential if it had an e to the minus t. And that's this part over here. So you will have some DC offset. So I'm just including this in here because if you look at any power system, you do have to include the effects of DC offset. And any first order circuit, A e to the minus t over tau, that's the transient term that's going to go away. All right. So don't need to worry too much about that. But what we end up with is here is our final value. Our I lock rotor is equal to the square root of 2 V phase I Z in. All I need this for is I need to go from RMS to peak. So I've got to multiply that by square root of 2. Then sine of omega t minus theta z. That has to be the angle of the impedance angle, the L and the R, because that will affect what that sine wave is. And then you have this decaying exponential, which you characterize here. But what I'm more interested in is this steady state value. So remember that nameplate that we looked at the last class? It had a code. And this code is the NEMA kVA code. And what does it tell us? Oops. It tells us, whatever that code is, how many kVA per horsepower is required to start this particular unit. This is not what it takes to run it. This is just what it takes to start it. Because if we go back to our nameplate should tell us the full load current. So for this particular application, our NEMA code G tells us that for this 150 horsepower motor, I need between 5.6 and 6.3 kVA per horsepower. So I have a range of how many kVA I need. And what that tells me, because kVA, S equals the square root of 3, VI conjugate, I can at least calculate the magnitude of current. That's all I really care about is this magnitude of current. So let's take a look at this particular machine. NEMA Design B, 150 horsepower, 460 volt. It's rated at 163%. Nominal efficiency, which is really quite high, 96.2%. It has a NEMA code G for starting. And our value here is going to be here. So now what we want to do is we want to find a range of how much current this is actually going to take and compare that to that 163. So we pulled our 5.6 to 6.3. Now we're going to go ahead and calculate what that line current needs to be. So here's our kVA code. So kVA per horsepower multiplied by horsepower. We multiply that by 1,000 to go from kVA to VA essentially. So this is just a conversion. If you don't like, you can do it this way. This is equal to 1,000 divided by 1K. So it just cancels out the K. And this is our value that we're going to be. Square root of 3, V line, I line. That's just magnitude only. That's all I care about. For the lower limit, 5.6 kVA per horsepower, I'm pulling over 1,000 amps. For the upper limit, I'm pulling almost 1,200 amps of current. Now, keep in mind, this is only going to be a short period of time. So as long as your wire can handle 1,000 amps for 5 to 10 cycles, then it shouldn't heat up and it shouldn't be damaged. But it's that voltage drop that drops your contactor out. That's where the issue is going to be. Okay. So this is a pretty typical one, and you can take a look at the range. So it's between 1,050 to 1186. It's 163. So you can do the percentage. 1054 divided by 163, 1186 divided by 163. Let's look at the percentages. So let's see, we have 1054 divided by 163. So 6.5 times, or 650% of the normal full load current, or 1186 divided by 163, 728% of the normal full load current is what this thing draws. And it used to be that you had these things called auto transformer starters. And do you remember when we talked about this the other day, where we said you just reduce the voltage, and there you have it, the voltage is down lower, so that means it pulls less current under locked rotor conditions. That's an older way to do things. A newer way is a variable frequency drive. You just tell it what you want to start with and how to ramp it up, and it does it much more effectively and efficiently. The auto transformer eventually will be shorted out, so it won't affect overall efficiency, but you're kind of stuck. And usually you set it, you can tap it, and there's like 65% of voltage, 80% of voltage. You can do it that way. It's very effective, very cheap, but you can do it that way. And the last thing I wanted to talk about.
Paul, are motor starters the same thing?
Same thing as what?
Or well, I guess where do motor starters come in? I've seen those pop up when I search, like instead of VFDs, if you just wanted to spin at synchronous speed, or
Close to synchronous speed?
yeah, with like, I don't know if they're actually for induction motors, but you can I see them frequently used, right? Like that stuff. I mean, are those for induction or?
Yeah, so almost all motor starters would be for induction motors. You wouldn't have a motor starter for a synchronous machine. It wouldn't work that way. That's pretty rare. So literally, you can go and you can buy this in a single box, and you can look at it and take a peek at it. And it's basically a big old contactor with some adjustable, I don't know if you can see over here, you can adjust some trip settings in here. Those are called thermal overloads, where they would trip if the current was above, was above a certain value for a period of time. You could go ahead and cause that to trip. And so this is a device that you would use to start a motor. The stuff that I've done, because I've done, it's been a while, but what I would do is I would, a 480 volt motor control center, which basically has, let's see if we can find one, which has all these devices, but it has many of them. So let's see if we can find an actual, here we go. This one, the door is open. So each one of these is just a very simple, basic. This one might not even be a motor starter. I can't tell. They're pretty small. But typically you would see, well, this has got a main breaker. Let's see if we can find one that's a little bit easier. This looks like, yeah, so this one has some breakers here, and then it also has some start-stopping capability. So it's all in one convenient lineup. So if you have 10 motors or 5 motors you're trying to start, you would buy this low voltage motor control center that would take care of multiple motors and work extremely well. So a starter would basically energize that. The VFD would actually be inside the motor control center typically. It's where you'd find it. And I've seen these things, you can have them 15 sections long. Just go on and on and on. So if you were to go to a process control place, like if you go to a paper mill, they have motor control centers in these rooms. Sometimes they're out in the factory, and they might have, 10, 15 bays where you're starting and stopping motors. Very efficient, very effective way to do things. It's like, it's just electrical distribution, but more specific for motors. And some of the other thing too is like, you have spaces in here where you can run cables, you can run power cables and control cables. Because if you got to run stuff over here, you can't go in this compartment because that's being used for something. So this compartment here would typically be routed for wiring. And good electrical practice is we have some control wires that maybe we want to stop something remotely. And remember that stop, we saw that CPT was only 120 volt AC. We would isolate 120 volt from 480 volt. So we would run those in different raceway to make sure that people don't mingle too much with that stuff. And then you can change stuff where you can have wiring coming in overhead or below ground. Which do you think is best? Below ground? If you're smart, below ground is the better because it looks really clean and neat. Right? You got all the wiring coming up. The
Above
problem
ground
with
is
that,
easier
though, is
to
you really
repair,
have to
though.
think about pulling wire because you're pulling it underground. So it's cleaner and neater to do underground, but most of the time it's overhead because you can run cable tray or even conduit over your raceway and just jump in where you need to. So it's usually, in the field, that's how you want to do it, but it depends on what you're looking for in terms of layout. Okay. That's all I had. That's all the stuff on induction motors. We did a lot, but it is the workhorse. It is really, it just does so much, and you'll see them everywhere. You go to any industrial facility, that has a decent size, even the fans, you'd be better off to go with using induction motors. If you were to go to Walmart or whatever, or even like we talked about where we have 3-phase for the dishwashers, more than likely those dishwashers are 3-phase induction motors that circulate the water because they're so simple. They're so cheap. If you were to compare a 10 horsepower motor with just about any induction motor with just about any other design, it's so simple and basic. It's just the way to go. So that's why they're predominant. And that's why when we look at nameplates or we look at buying stuff, they're a dime a dozen. You can buy them. You can't buy them at Home Depot. Anybody know why? Because how many of us here at our house have 3-phase power? Home Depot is more of a consumer, right? A consumer use. So they don't sell a lot of 3-phase stuff because there's no demand for it, because none of us have 3-phase power applications. The only time you'd see the end consumer, like an average person that would use 3-phase power, is maybe they're really into high-end woodworking or metalworking, where you need, better quality lathes or power saws, whatever. So if you're pushing something, you don't want it to wind down, those would be using 3-phase motors, not single-phase. You can only get to a certain power level before you have to switch to 3-phase. And again, just the maintenance on them is nothing. They're easy, they're cheap. So, it's hard to find stuff that runs single phase. The biggest ones you'll see single phase in a regular facility, it's kind of wacky to say this, but elevator motors. Elevator motors would be like your highest, maybe 5 or 10 horsepower to hoist, however many people up and down a couple flights of stairs. But I think they're limited to, once you start going, I don't know if it's 3 levels or 4 levels, the motor just has to be so big because you got all that cable, you got to be able to move it up and down. So once you start getting above that, you got to start going with 3-phase applications. So that's why when you're in New York City, you see those elevators, and those elevators, anybody ever been in a high rise? Those elevators are fast. So those are big motors. Those are 3-phase motors. And they just work. They really work effectively. Those are a little more complicated than just a simple one, because what happens when you get to the floor, you got to wind down the speed, and then you gotta lock it in position. So they have a brake on those. They have a bunch of different characteristics that make that work. So what I'm saying is that's not just a simple induction machine. That's a little bit different. But so questions, because up to this is going to be on your test, which is a week from today, right? During class. So Wednesday at noon, let me know if you want to take the class in person or remotely. We'll do a review session on Tuesday with whatever questions you have. Unless you have questions now, we have a lot of time. I didn't think I'd go this fast, but I went reasonably fast. So any questions? Feel pretty good about this stuff? Getting better? The other part too is more than half this class, this is the first time we've had me for an instructor. So getting a feel for how I do tests and what to expect makes it a little bit, it takes some of the fear away, I would imagine. So, but the reason why I like teaching this stuff is because, a lot of folks, this is what we're going to be doing in industry. Like it or not, a lot of our students end up working in the utility type industry. They go work for, the TRCs, the powers, the RLCs, the SGCs. That's the type of stuff they do. Even the folks that went to North Carolina, they're doing a lot of this stuff and understanding the three-phase power stuff, because I would imagine if it's a big enough facility, they've got to understand three-phase, so sizing cables and making sure voltage drop is sufficient. Those are pretty darn important things that you would do. I don't even know that David's company, what did you guys do? Did you get really big buildings? Is that what it was? Or didn't you go to North Carolina, Austin? Oh, this summer. Okay.
I actually didn't do like any engineering while I was down there. A lot of the work that I did was just design. They just kind of like our program. Also, they like that we do project management, but
Oh,
they
okay.
don't do a lot of the engineering. They outsource that.
Ah, okay. Well, maybe you won't do this then. But I will say that most of the engineers that the ones that I'm familiar with, they're all expected to do engineering design. Project management is obviously a really good skill to have, but it's hard to be a good project manager when you're not really sure what it takes to go into a project in terms of how long does it take to design a substation or a new building? How can you project manage something if you don't really know how long it takes, or how long it takes people, or how many people it takes to do a specific task? So what I always found is to get good at project management, you just have to work for a while and get a feel for how long it takes to do things. Now that's to say you can't do it, because sometimes you can have somebody else develop a schedule and have somebody else develop, like lists of percentage complete, and then you just keep track of stuff. But to me, I don't know if I need to be an engineer to do that. If I'm just updating a spreadsheet, I don't know if that's needs really an engineer. That's not a criticism. It just seems like you could hire people at a much lower billing rate than an engineer to do that type of stuff. That's my impression, but I don't know. And I think also too, engineering students tend to be, harder workers, maybe. I don't mean to be, I don't want to put people down, but it's just, you got to work hard to do well. And so when you get out, you've sort of proven that you're a pretty hard worker. So companies are willing to work with engineers because probably a pretty darn hard worker. But the whole world is out there. So take a look, try different opportunities. I know what you all did in North Carolina was really good. Maybe you might want to go back. Maybe you want to try, hey, I'd like to intern at a different place. A quality company will say, I perfectly understand. We want you to be happy here. But if you love to do the work, then you might as well just go back to where you were. If there was really interesting work and you enjoyed it, head back there. I personally like variety. So I was always really enthused by, this is a completely different project. So I'm going to learn something different and new. So I really like that, but that's where you all get to find your own way. Questions? Okay, so for Tuesday, what are we going to do? Review, come ready with any questions. It could be, how do I do the homework problem number 1? Explain number 2. How did you do this? Can you explain this MATLAB? Whatever questions. You do have the exam 3 review. That's already available, right? So you do have that chance to go through that. Anybody have any comments or thoughts on that yet? Like I said, this is the first attempt with interacting with or working with a student to give me some tips on my first revision. So hopefully it's improved and it's a better to use document. TV Land, any questions?
Not right now.
Go ahead, Eric.
I was gonna say, I was gonna ask about the, on the last homework, I think it was like the stator magnetic field versus the rotor fields.
Yep. Yeah,
And-
so remember in an induction, geez, I can't talk. In an induction machine, okay, the stator field, whether that's coming from a synchronous, if that's a synchronous machine or an induction machine, the stator field is the same. You're getting currents, you're getting current flow, which is getting you to have those magnetic fields on the stator. In an induction machine, the rotor is spinning at a lower rate, particularly if it's an induction motor. The rotor mechanically is spinning slower. And because you got a set of shorted windings, you've got a changing magnetic field in a short circuited or a loop set of windings, you induce a current in those windings. And that current is AC. So now that I've got an AC current flow, I'm going to produce a rotor magnetic field. And that's going to rotate exactly the same as the stator, right? We have an AC, so that's spinning along whatever the synchronous speed would be from whatever that AC frequency is. It just so happens that AC frequency, the rotor field that it produces, or the speed of the rotor field, added to the mechanical speed of operation, makes it so that it runs at synchronous speed. So your rotor magnetic field is spinning at exactly the same speed as your stator magnetic field. But the rotor itself, especially like I said in an induction motor, is going to be spinning slower. And we want that. We want the stator field and the rotor field to be spinning at the same speed, because that's how we get constant torque. If they were relative change, sometimes the magnetic field attraction would be stronger, sometimes it would be weaker. And that would mean we'd have variable torque, which we don't want. You can ask our mechanical engineering friends. The last thing you want to do is to see your torque going up and down on a fairly regular basis over a cycle. You don't want it to go up and down. That causes vibration, which usually damages motors pretty quickly. So, Eric, does that answer your question?
Yep, yeah, that was kind of the missing piece I was trying to figure out. So it was
Okay.
with the actual shaft plus the other field.
Yeah, that was the bug concept, right? When we talked about the sun rising in the east and setting in the west.
Yep.
Is the sun really rising or are we rotating? So we're moving at 1,000 miles an hour, but if I start walking in the direction of rotation, maybe it's 1,004, right? But it's just my reference point. I'm rotating along, but from the sun's perspective, I look like I'm spinning a little faster. So it's the same concept.
I did have a second question.
Go ahead.
So when you initially turn a motor on, if you were just using a contactor, you have a large inrush of current.
Yep.
So if you had that connected to a VFD and ramped it up, does that, I guess, reduce the inrush that you would
Yes.
have to deal with?
Yep. So what happens is, remember, you get all that. Remember the frequency when we did our locked rotor test, we ran it at 15 hertz. And that effectively reduced our reactance. It's the same thing. And a variable frequency drive can also change the voltage. So it can lower the voltage. So you can change it so that not only do we have a lower frequency, but we also have a lower voltage.
Okay, cool.
So the variable frequency drive does both.
Okay, thanks.
And now you can buy 3-phase variable frequency drives for $400. They're pretty cheap. Power electronics have gotten a lot cheaper. Yes, sir.
One thing would be, there's mention of students know how to read one of their inputs.
Yep.
Is that just knowing like where to look like the
NEMA design stuff, looking at the horsepower, the number of poles, all those things to be able to do the calculations. Yes, sir.
So when you give us the class where it has a different input, is that what we can write down?
I will tell you that, or you can just put down, assuming they're the same. That would be fine. Any other questions? All right, have a great weekend, and I'll see you all on Tuesday. Take care, everyone.
Thanks, Paul.
Thanks.